Alright, so in this lecture I want to discuss some homework questions with everyone, because in the past most students had questions about these problems. I wanted to discuss them with everyone. So this is homework 3. The first question we want to discuss is question 5, 21.86. Okay. Electric field from a continuous charge distribution, as I said, it's one of the hardest parts in this class, because you have to use a different tool. You don't just do algebra, you do calculus. Okay. So let's take a look at this question. A semicircle, okay, has been charged. So the right half, okay, so this part is charged with positive Q, okay, oh no, negative Q. So the right half, so the left half is positive Q, has been charged with positive Q. Now we want to find the electric field at the origin produced by this whole thing, okay, this distribution of charge, right? So we want to find the electric field at this point, okay. So remember, our theory is this. We always start with the theory we learned for point charge, right? For any point charge, the magnitude of the electric field created by this point charge, this source charge, at any point, the magnitude is going to be this, right? Direction, if the source charge is positive, away from charge, the arrow away from charge. If the source charge is negative, the vector is toward the charge, okay? So now let's take a look at this. We're still going to pick an infinitesimal, an infinitely small charge, okay? And then draw the electric field created by this very, very small point charge and start from there. And sometimes there will be a symmetry, and there's a distribution you can use to help you get rid of some components, okay? So that's the idea. At the end, the electric field, it's going to be the integral, the vector integral is going to be reduced to a scalar integral, right? Remember, if I generate this to a multiple charge combination, okay, it's going to be this, right? If I have a group of point charges, isolated point charges, I just calculate the electric field created by each charge using this theory, and then add them as vectors. So of course you're going to break them into x and y components. And then if I have a continuous charge distribution, this summation, because you're adding together an infinite number of small e's, so summation becomes integral, okay? So this is still vector integral, so you should still do it in x direction and y direction separately, okay? But sometimes you can use a symmetry in the problem, okay, to get rid of one component, okay? So let's apply the same theory in this problem, okay? So now I'm gonna pick infinitesimal charge, very, very small, infinitely small charge at some point, right? Doesn't matter which point you pick, okay? Say I want to pick this piece, okay, very, very small piece. So this is positive, right? How do I find the electric field created by this very small piece I pick? Well, first of all, this is going to be positive, right? So the electric field is going to be away from it, okay? So if this is I call E1, right? This is Q1, okay? Now you see that, okay, there is a symmetry you can use, right? For example, I can pick another charge on the right, okay, which is going to create an electric field. So in this case, this is going to be negative, if this is what I call Q2. So the electric field should be toward this charge. Now you see the symmetry, right? So that means for any small piece I pick on the left, I can always pick another charge on the right, okay, pair it up with this guy, And then if I break these two electric fields into X and Y, so Y components are going to cancel, right? Because if you break EY into X and Y, you get this, E1X, E1Y, right? You break E2 into X and Y, you get E2X, E2Y. So, and then if I make sure Q1 equals Q2, right, they're infinitely small, so of course you can assume that they carry the same amount of charge, are very, very small. And then I make sure this, the distance between this charge to the y-axis is the same, so you're going to get all these angles the same, okay, the magnitude is the same, so y and y components cancel, right? So you're going to be left with x components. And then you just add these two x components, right? And then because this is a semicircle, so for every point, every little charge you pick on the left, right? Like I pick this guy, I will have an electric field in that direction, but I can pick another guy on the right, totally symmetric to it, and then it's going to have an electric field in that direction. Again, y components cancel, only x components left. And then the x components, they are all in the same direction to the right. So all the x components add. So you can literally just add all these x components. So in this case, we know that the electric field is still going to be only in x direction in this problem, right? So I only have an x component. Okay, so that's the direction, right? And we figure out what about the magnitude? Well, then you still need to do this integral, right? But in this case, you only need to find the x component of the net electric field, which is going to be integral of this dx. Okay. Now let's see. So then you would have to find expression for this ex, right? dx. Now you're just going to pick a de. Now I'm going to redraw it, okay? So all I need to do is pick a dq somewhere, and then start from there, find expression for dx, and then just integrate that. And again, our goal is to reduce this thing into one variable. You may have a few variables to start with, okay? You're going to write everything in terms of one variable, then you look it up in the integral table, you can find the answer, okay? So, like say I'm just going to call this guy dq, and then this guy has an electric field at this point, de, right? And then I only need this x component, I don't need the y component, because I know that all the y components are going to cancel out, okay? So I only need to find expression for this dex. So this is what I want, and then I'm going to plug in and then write it at the end, write it in terms of one variable, okay? And then dex, so it's just going to be, again, from this diagram, I know that if I want to find expression for dx, it's just going to be de times, you can pick any angle you like, right? For example, if I pick this angle, so that's going to be cosine theta, right? So that's going to be d cosine theta. And then you can put in here, so this guy is going to be equal to de cosine theta, right? And de, I know how to write it, okay? So that's going to be ke dq, we have done that before, r squared, now cosine theta. Right. Now let's see if there's any constant we can pull out. Now ke, you can pull it out, right? Now this r is going to be the distance from the charge dq to the point you want to calculate the electric field. And then you can see that for any charge you pick, this r is going to be the same, right? This is the distance r. This is distance r, which is going to be just the radius of this semicircle. In this problem, it's a. So okay, so that means this r is not a variable. You can take it out. Okay, so you're going to have dq cosine theta, right? Now, okay, so you still have two variables, right? You have to find a way to write these two guys in terms of one variable. So you have like a function of x times dx. You integrate this thing, then you can just look it up in the integral table, right? Now this dq, we have done them many times, right? If it's one-dimensional charge distribution, you can always write this dq as the linear charge density times the very, very small length of this point charge you pick, right? Because this is lambda e is just going to be q over L, right? So intuitively, as I said, right, if this total charge is 10 coulombs, the total length is 5 meters, right? How do I want you to find the charge on a very, very small length, 0.00001 meter segment. How do you find the charge on it? Well, I would divide this by the total length and multiply it by the very small length of this piece I pick, right? That's how I find the charge on this very small piece I pick. Now we just use symbols, okay? And this dl is infinitely small, okay? Infinitely small. So that's how I write dq, right? So in this case, again, you can write this dl as dx or dy, right? We have done the rod, right? The rod, because it's totally vertical, so the dy we can write it as dy. The dl we can write as dy. Now in this case, well, let's continue here. So I would have ke over a squared lambda e. All right, so I have dq equals q over L dl, or lambda e dl. So lambda e times dl cosine theta. So lambda e is a constant, right? It's a density, charge density. If this is uniform charge, the charge density is going to be a constant. So you can take it out, but you still have dl and cosine theta, okay? You still have two variables. You can integrate them. You're going to write them as a function of one variable. So the trick is this. If you still remember the definition of the angle in radians, okay? Okay, if you still remember the definition of angle in radians, if this is the angle theta, right? And this angle corresponds to an arc length S, right? And a circle with the radius R. So this theta angle in radians, which is the SI unit of angle, it's going to be equal to the definition of theta angle in radians is the arc length divided by R. Right? So that's the definition for this theta. Okay? Now what we're going to do is this. Okay? Now imagine this guy we pick. We zoom it in. So this is the small dq we pick, okay? If this is a small dq we pick, we zoom it in, okay, so we know how to work with it. Then the length of this guy is just going to be dl, right? The arc length is dl, that's the length of this dq I pick. So this r is just going to be the radius, right, of this semicircle, which is a, okay? Now this theta angle is just now I'm gonna call it d theta because this is an infinite small angle, okay? So I would have this, d theta in radians, it's gonna be equal to dl over a, right? Why do I do that? Now I can write this dl in terms of d theta, right? Arc length equals the radius times the angle. If you rearrange this equation, arc length is going to be equal to radius times the angle. But now we're just dealing with the infinite small arc length, infinite small angle, okay? Now you can see that once you write dl in terms of theta, now you will have one variable, right? One function with one variable here. Now you're ready to evaluate that, okay? So at the end you will get, okay? I'm going to continue here. take out KE over A squared, lambda E. Now I would have A d theta cosine theta, right? Now you can even take out this A, right? Because this is a constant, so you would have KE over A squared times lambda E A cosine theta d theta, right? So this A cancels out one power of this A, so at the end you will have KE over A lambda E cosine theta d theta, all right? So that means, first of all, you need to find lambda. The problem doesn't give you lambda, but remember the definition of lambda E, total charge divided by total length, okay? So the lambda E is going to be the same in either the left half or the right half, right? So the lambda E in this case is just going to be, if you pick this left half, the total charge is Q. What is the length of this left half? What is the length of this guy? That's going to be 1/4 times 2 pi r. Right, that's 1/4 of circumference, right? So that's going to be expression of the lambda E. I'm going to plug in at the end. Remember, the problem only gives you big Q, little a, right? So you have to use these two variables and other constants, right? You can't use like, you don't have lambda E in the problem. You don't have this total charge and total L in the problem. Okay, so that's going to be the lambda plugging at the end. Now this cosine theta, d theta, you can look this up in the integral table. This is very easy. This actually turns out to be a sine theta. Okay, now you're going to figure out the bounds. Okay, so let's go back to this diagram we drew. Okay, so the theta angle, you see that it's going to be, so, well, first of all, I know that if I pick this charge dq here, I can always pick this charge on the right. So no, let's rejoin. Okay. Okay. Now I know that this is the semicircle. This half carries positive Q. This carries. Now we have already figured that if I pick a charge here, this is going to be the electric field, right? And I can pick another one which is symmetric to that charge, and then the electric field is going to be in this direction. And then these two electric fields, they're going to cancel y components, only x components are going to be left, right? And if I'm only interested in x components, right? So this guy is going to have a e1x, right? This guy is going to have a e2x, right? Then this y components cancel out. We figured that. So these two guys cancel out. So for every single piece you pick on the left, you can always find another one totally symmetric on the right, which is going to have the same x component in the same direction, the same magnitude. That means if I want to find the net electric field in x direction of this whole semicircle, all I need to do is just find the net electric field x component of the left one, left half, and then double it, right? Because this half is going to provide me this two halves, right? Each half is going to give me the same component in x direction. So all I need to do is this. Because this charge and this charge, at the end, they're going to give me the same x component in the same direction. So all I need to do is this. Erase this guy. Just figure out the electric field, total electric field created by this half, x component. I only need the x component, right? And then double it. I will get the total electric field created by this this semicircle. Okay? So that means all I need to do, if I want to figure out the this, I would just figure out the bounds of the theta angle from this dq to this dq, right? So those bounds is going to be from 0 to 1/2 pi radians, or 90 degrees, right? So all I need to do is this, right? So this guy is going to be, again, it's going to be 2 times this half, so it's going to be 2 times this theta angle from 0 to theta angle from to 1/2 pi radians cosine theta d theta, right? So I only need to calculate, so this is only going to be the x component of the electric field created by this left half, or the right half, doesn't matter, okay? And then you double it, you should get the x component of the net electric field from this whole semicircle, okay? So I'm gonna stop here, I'm gonna leave the rest for you to finish. Okay, so this is this question. Now, the next one, the next question, it's also a continuous charge distribution, one-dimensional. Okay, it's a rod. Okay, it's a rod. So but it's a little bit different than what we saw. Now let's take a look at it. Now there's already a coordinate system set up, x, y. Now there's a rod here on the x-axis, right? And this guy has been charged positive Q, okay? So this whole thing has been charged positive Q, okay? So that means this guy has a lot of positive charge on it, uniform distributed, okay? I want to find the electric field created by this source charge at a point here. Okay, I want to find the electric field created by this guy at this point. And then once I find the electric field, I'm going to place this test charge little q there to find the force, right? But finding the force, as I said, it's going to be the easy part, right? Finding the electric field is the hard part. So let's find this electric field. So we know some distances here. So this length is A. This is going to be B, right? Now, how do I find the electric field at this point? Okay, the same theory. Okay, I'm going to still start with the theory for point charge. Okay, pick infinitesimal charge here, like this guy. Okay, and then what is the electric field created by this guy at that point? I want to calculate. Well, that's just going to be in this direction to the right, right? Because positive source charge away from it. Now you're going to pick another one, right? Because sometimes you may have, because you always get a vector integral. Either you break it into x and y, right? You do E net x equals this, right? E net y equals this. So that's what you should do, okay? Theoretically, but sometimes you can use the symmetry of the problem, just calculate one of them, because you can figure out the other one is 0, right? If you cannot, well, just repeat the same process in x and y, right? The steps are the same, okay? The only difference could be just like the angle or something, okay? Now let's see, okay, but this electric field is already in x component, in x direction, right? What about the other one? If I pick another one, this guy, okay? So what about the electric field created by this guy at this point? That's positive charge, positive source, is still going to be in the same direction. Okay, so that's very nice. That means I don't even need to use any symmetry to get rid of one component, because all these electric fields created by every single infinitesimal charge I pick, it's going to be in the same direction. So I can just literally add them together. if you add them together, there's an infinite number of electric field. You don't just add them, right? You do an integral, okay? So it's still gonna be this, right? So I don't even need to use any symmetry because the problem doesn't have any y component for this electric field. So there's no y component, okay? So you see that I'm gonna still have this expression, okay? Now this doesn't change. Now I'm gonna start from there. Now in this case, I don't even need to do cosine theta, sine theta because the electric field is already in this x direction, right? So I would just call this guy dq. The electric field created by this guy dq. dq, this is dE. Let's just find the electric component of this dE and then just integrate that. All right, so in this case, this is the x component, but the x component is just going to be the total vector because the total vector only has x component. Now, how do I find expression for dE? Well, okay, again, ke, right, dq over r squared. That's the theory for any point charge, right? An infinite small charge. Of course, you can treat it as a point charge, single point charge. Okay, and now ke, you can take it out. Now you have dq over r squared. Now this r, remember this definition of this r is from the dq you pick to the point you want to calculate the electric field, right? In this case, it's not a constant, right? Because if I pick this as the dq, this is going to be the r. If I pick this guy as a dq, this is going to be r. So r is a variable. It's not a constant. You can't just take it outside the integral. You have to leave it inside the integral, okay? Now we have dq and r squared. We have two different variables. We want to write them in terms of one variable so we can just integrate it out, okay? So the trick, again, this dq, okay? We have worked with that many times. Now I know that the dq, you can, if it's a one-dimensional charge distribution, you can always write this as linear charge density times dl, which is the length of this very, very small piece you pick, right? The length can be 0.00001 meter, doesn't matter, okay? Now the lambda e is going to be the q over l always. But you should be careful. Does the problem give you the total charge or total L, right? These two guys, they mean the total charge and total length. Not always there's a big Q in the problem. That's going to be the symbol I use. If there's a big L in the problem, that's the symbol I use, okay? You just need to find out the total charge and total length of this charge distribution you're given. So in this case, let's see. The total charge is the Q. So that's going to be the symbol I use, right? What about the total length of this charge distribution? That's A, right? So that means at the end, the lambda E is going to be Q over A I plug in, right? Okay, because the problem doesn't give me any L, okay? So these are the two symbols I'm going to plug in at the end. So, and then this dl, now in this case, you can write this dl in as dx, right? Because this guy is on the x-axis, right? So the length of this small piece is just going to be the dx, right? So it's just going to be the length in the x direction, okay? Because it's not an arc. It doesn't have an angle with the x-axis. So I can just write this guy as, so the dq, I would just write it as lambda e dx, okay? Or you can just carry this q over a if you like, okay? But I'm just going to plug it in at the end, right? Okay? So I have ke lambda e dx over r squared, okay? Of course, I can take out this lambda e. So it's going to be ke lambda e, now dx over r squared. Okay, so I have an x, I have r. So I should write them in terms of only one variable. I can't have two, right? So let's see if I can write this r in terms of x, okay? So let's focus on this guy. If I want to write this r in terms of x, I should know the definition of r and x, right? R is defined as the distance from the charge the point charge you pick to the point you want to calculate. So it's this. What is the definition of the x for this charge? Well, the x, if this is origin, right? The problem already set up the origin for you. If this is the origin, okay, the x coordinate is just going to be the distance from the origin to this charge, right? So if I want to draw, this is going to be x. Right? If I say this guy has an x coordinate 5 centimeters, it's just telling you it has 5 centimeters from the origin, right? So this is what x means, okay? So that means I can write this r in terms of x, right? Okay? Do you realize the relation between these two guys, right? So even if you pick a different charge, right, you're going to have a different x, you're going to have a different r, both of them are changing, but what about the sum of these two numbers? It's always going to be a plus b, right? You pick this charge, this is going to become x, right? You pick this guy, this is going to become x, and then this is going to become r. X plus r equals a plus b. That's how I found the relation between them. All right, so once you have done that, so how do I write this r in terms of x? A plus b minus x. So r squared is just going to be this thing squared. So at the end, I get this dx over a plus b minus x, this whole thing squared. Okay? Now what about the bounds? Okay, the bounds is going to be the lower bound and the upper bound of the x, of the x value on this charge distribution. Okay, so take a look at the rod. Okay, what is the minimum x value you can get on this rod? It's going to be this end, right? If you pick this charge, the x value is going to be equal to 0. Right, that's the minimum r, that's the minimum x you can get on this rod. Remember, you're integrating on this rod, okay? What is maximum value, well, maximum x value you can get on this rod? It's gonna be this end. You pick a charge on this right end, what is the value of this x? That's gonna be a, right? So the bounds for this x, okay? It's going to be from 0 to a. Okay, so now you can finish this integral, right? You look it up in the integral table, okay? So you should find something similar to this in the same form, okay? So you should find something, let's see. It's going to be one of these integrals. So I want, okay, I see that. It's going to be the fifth, okay? It's going to be the fifth, okay? But you're going to match every symbol with this integral fifth, okay? And this integral table I posted on Sakai. So I'm going to write it. So in this integral, okay, we know that 1 over x plus a, but this is already, there's already a, so I'm going to change this constant in this integral. So whatever this is, right, let's call it c squared equals negative 1 over x plus c. So compare this with this, okay? How do I match this with this general conclusion? So you can use this conclusion to evaluate this integral and then plug the lower and upper bounds so you can get the final answer, right? So I can give you some hint. You can actually write this guy, because you want to write this guy as x plus a constant and then squared, right? So you get this. Ke lambda e. Lambda e is going to be q over a I plug in at the end. So how do I write it in that form? Right? I want to write this integral in this form. 1 over x plus c squared equals negative 1 over x plus c. Okay, so that's the integral. So what I could do is this actually, dx at the top. Oh, dx at the top. Okay, I forgot the dx. Okay. So then I can write this. First of all, this thing minus x squared is going to be equal to x minus this square, right? Because the square is going to take care of the negative sign, so it doesn't matter you do a plus b minus x or x minus a plus b. All right, and then I'm going to do this. So I know how to match this with that, right? So that actually becomes x plus minus a plus b x plus a constant squared at the bottom, x plus a constant squared at the bottom. Now you can match everything and figure out that integral, plug the upper and lower bounds. You can find the electric field, the magnitude of the electric field. Okay? And then once you find the electric field, the force is going to be easy. Okay. So this is this question. Now let's take a look at the last one, question 13, 21.78. Okay. I'm going to erase this. Okay, the last question is the I want to discuss with you is the last one in homework 3, 21.78. So this is a question. Okay, a charged object with the initial velocity horizontal, so that's the initial velocity in x direction, right? Enters the electric field, uniform electric field created by two parallel plates, and the electric field is down. It's deflected down, so I know that it's going to be positive charge, right? If it's negative, it's just going to be deflected up, okay? So in this electric field, so it's the same as the question we discussed in the previous lecture. It's just going to be projectile motion, right? Exactly projectile motion with a constant acceleration, constant force down, nothing horizontal. So, but it doesn't stop here, right? So it's going to continue moving. So outside this region, so if it's outside this region, there's no force on it. And the problem says ignore gravity and air resistance. So literally after this region, there's nothing on it. If there's nothing on it, it's going to keep moving in a straight line with a constant velocity. Which law is that? Newton's first law, right? Newton's first law. So there are two different motions here, right? This is a projectile motion, so it moves in a parabola, not in a straight line. So this is not a straight line, okay? It's deflected down, but after that point, it has left this region. This is the straight line motion, okay? Constant velocity. So the problem tells you this length, horizontal direction, is 26 centimeters. Well, you may get some different numbers, but these are the numbers I got. Electric field is given 800 newtons per coulomb. Initial velocity in x direction, of course, initial velocity in y direction, in this case, is going to be 0, right? And then this distance in x direction, horizontal direction, is 56 centimeters. So we don't know the distance travels in this region or this region, but we know the combined displacement. The problem tells you the combined displacement in y direction, in vertical direction, is going to be 1.45 centimeters. So actually what we know is this. There is a vertical displacement in this region, right, in this projectile motion, and there's another displacement in vertical direction and this straight line motion. And the problem only tells you this. The sum is going to be this number, right? So that's what we know from the problem. And the question is this. Calculate the object's charge mass ratio. So we want to find this guy. Okay? So a lot of people, they would say, oh, I don't have the charge. I don't have the mass. I don't know how to find the charge mass ratio. Okay? If you already have the charge, if you already have the mass, right? I don't even need to tell you such a long story. Just put them together, divide them, give me the number, right? That's algebra, that's not physics, okay? So if we get a problem like this, that means we don't have the charge, we don't have the mass. That means you cannot solve this problem directly just by finding the charge mass from the problem. You may need to connect them to something else. Right? If I can find expression for this charge mass ratio, and then I know all the numbers in this expression, then I can find the charge mass ratio, right? I don't need to find literally the charge, the number for the charge 5 coulombs, for the mass like 2 kilograms, and divide them, right? As long as I find expression for them, I can connect them to some other variables I know from this problem. So I can find that. Okay, so let's see how I can find the charge mass ratio. How I can connect that to something I know this problem. So let's first take a look at the projectile motion, right? And this projectile motion, I know that there's a force in the vertical direction, which is down, right? So if I want to use the theory we learned, Newton's laws and the kinematic equations, so the acceleration in y direction would just be net force in y direction over mass, right? And then it's going to be, in this case, it's just going to be the net force of the electric force in y direction, because the electric force is only in y direction, and that's the only force on it. And how do I find the electric force? That's going to be charge, and it's a positive charge, so I don't need the absolute value sign, times the electric field divided by the mass. Now I do see charge and mass together here. So that means I can connect the charge mass ratio with the electric field and acceleration, right? So you see that if you rearrange that, you would get, so I just get AY equals this. If you rearrange that, you will get the charge mass ratio is just going to be equal to AY over E. Right? You see that? That's how I connect it to something I know in the problem, or I can find in this problem, right? So I can do kinematics, I can use Newton's laws, and then find the acceleration in y direction and divide by the electric field is given. Okay, so this looks promising. I only need to find the acceleration in y direction in this region. Then I can go ahead and divide that by the electric field. That's what I need. Okay. So how do I find the acceleration in y direction? So we can use these kinematic equations, right? So in y direction, there are 3 kinematic equations I can use. Which one do I pick? Well, it totally depends on what numbers I know from the problem. I know the sum of these 2 displacements, but at least this guy is connected to AY, right? So maybe I can make use of that. Okay, so let's see. How do I connect this displacement in y direction and this region with this AY? Well, that's the second equation, right? The second equation is this. Plus AY theta t plus 1/2 AY theta t squared. And in this question, because it's the initial velocity in y direction is 0, right? So, oh, not AY, this is Vy, right? So this is 0, and then if the difference between them, it just theta Vy, theta y1, right? So theta y1 is just going to be 0 plus 1/2 AY theta t squared. Okay, so now you see that, well, I have some connections here, okay? At least I know this theta y1 is going to be equal to 1/2 AY theta t squared. So if I have theta v1 and theta t in the first region, I should be able to solve for AY and then just plug it in, right? Theta t, I can find it, right? Because as we did last time, you can always find the time. If you can't find the time in y direction, you can always do that in x direction, plug it back into y direction, right? That's the only number you can use in both x and y. So okay, so let's call it delta t1 because we only need the time in this region. Okay. So how do I find delta t1? Well, you can go ahead and use the second equation again in x direction. And actually, if the acceleration in x direction is 0, the only useful equation in x direction is going to be the third one, right? We said that last time. Now you see that the delta x is going to be 26 centimeters, right? 26 centimeters is going to be equal to vxi times delta t1. This is going to be 0 because the acceleration in x direction is 0, right? There's no force in x direction. Okay, so this is going to give me delta t1. Okay, good, because the initial velocity is giving the problem. So this guy, no problem. Okay, so all I need to find is delta y1. Okay, but I only know delta y1 plus delta y2 equals this number. If I can find delta y2 and subtract that from this right hand side, then I will get the delta y1, and then I can find ay and then go ahead and find charge mass ratio. Now let's move to the second process. This is actually easier. This is a constant velocity motion. Nothing changes, right? The velocity is going to be constant in this direction or in x and y direction. So if I want to find delta y2, obviously, well, it's going to be the second equation, right? And then the acceleration is going to be 0, so it's going to be vy delta t2. Now I'm going to use delta t2 because I only need the timing in the second process to calculate the displacement in y direction. And this is just distance equals velocity times time. That's intuitive, right? Something is moving with a constant velocity. Distance equals velocity times time, right? Nothing changes. So if I can find these two numbers and multiply them together, I can get this delta y2. Then I can go ahead and do that. Now delta t2, okay, let's see. Delta t2, you can again find it in x direction like we just did, right? Because in x direction, you already know the distance. So in the x direction, you will also have this. Delta x2 equals vx delta t2. Delta x2, it's going to be 56 centimeters, right? So you get 56 centimeters equals. Now, what is this velocity in x direction? Well, that's going to be the same all the way back to the initial point because the velocity in x direction doesn't change here. Doesn't change here, okay? So nothing changes in x direction. In x direction, you break it down, it's just going to be moving in the same direction, the same velocity, and reaches this collecting plate. Okay, that's why I will always break it into x and y. Okay, so in x direction, you're still gonna do this. Distance equals velocity times time. Distance equals velocity times time, right? Because in x direction, nothing changes. So you will find delta t2 using still that equation in x direction. All right, so I will have this delta t2. Okay, it's very promising, we're getting there. So the only thing I need is this Vy so that I can do all the algebra and until I find the charge mass ratio. How do I find this Vy? Okay, remember the Vy, I don't put an initial final here because in this process Vy is gonna be the same, right? Because in this process nothing changes, it's straight line motion, constant velocity in both x and y directions. But how do I find this Vy, right? Remember, where does this Vy come from? It actually comes from the velocity this particle has when it exits this region. So when it exits this region, it already has a Vyf at this point. Of course, it also has a Vyi, a Vxf at this point. But that's going to be just equal to this initial velocity, right? So what changes is going to be the velocity in y direction, because initially it's 0. And then it's going to be changing. It's going to actually speed up, right? It's going to be accelerating in y direction because there's a force in y direction. So that's pretty much like the gravity in y direction, right? How do I find this VYF? That VYF, it's going to be the VY I plug in the second process, right? Because in the second process, it's just going to carry the velocity it has when it exits this, the first region. So this guy is going to be the value I plug in. How do I find this VYF? You're going to still use the kinematic equations, right? Because this is the first process, right? The first process in y direction is a constant acceleration motion. So you would just do Vyi plus Ay theta t1. And Vyi is 0, right? So this is just going to give you Ay theta t1. Okay, so let's see what we get. So this theta y2, I'm going to rewrite it here. Theta y2 equals this Vy, which is what I just found, Ay times theta t1 times theta t2. So that's the complete expression for theta y2. T2 we can find it here, theta t1 we can find it here. So the only thing we need in this is Ay. So if I want to find theta y2, I need Ay. But wait a minute, I need this theta y2 to find theta y1 and then find Ay. Okay, so this is back to what I'm missing. So what do? Well, then in this case, you don't need to subtract theta y2 from that equation, right? Because you get this equation, theta y1 plus theta y2 equals d, okay? Our strategy is this: move this guy to the right and find theta y1, plug it back in to find Ay. But this guy also has Ay. Okay, so that's gonna be a different strategy. Let's just use this equation. Let's leave all these Ays here, right? So you will get a function of Ay on the left equals a number. Then you just rearrange this equation to get Ay, right? Because theta y1 we found is gonna be 1/2 Ay theta t1 squared. Now you see that you put these two guys together, you can use this, you rearrange this equation to find Ay, because both of them are functions of Ay. And once you have Ay, you can find the charge mass ratio, right? Because we figure the charge mass ratio is just going to be equal to Ay divided by E. Okay, so this is how we solve this problem. I'm going to stop here for this video.